But anyways, let's dive into the fun stuff. Last time, we were talking about some of the things that make up vision, light, everything that we know, everything that we see. Right? Many of those details, understanding that light is, well, it's in fact a wave. And like other waves, it has a lot of particular properties of how it interferes, how it travels, things like that. We also discussed some of the things like surrounding how we would have black body emissions. We get spectral lines just like this out of certain materials. And this slide in particular was one of the big ones that we were looking at. And I kind of brought this up, and there were some strange things that I saw, but not things that we necessarily brought up. Basically, what we saw is that when we have some object that is hot, we get some sort of spectrum of all of the different colors that comes off of it. Because there's a big difference between what we call thermal emissions and electronic emissions. Thermal emissions are essentially the full continuous spectrum all at once. Electronic emissions are very, 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 very specific lines. And I'm not using enough fairies there. I mean, very specific, incredibly specific. But this was one of those difficult things that we were grappling with for some amount of time. Because if you notice here, I've got these extra dotted lines in place here that I haven't really discussed too much. See, we know these solid white lines are essentially what we know to be there. These are the emissions that we have measured, that we have studied, that we have confirmed exist exactly like this. These dotted lines were two different guesses trying to understand how things lined up in the first place. What actually predicts this curve? What creates this curve? Based on all of our science and understanding, using a lot of different thermodynamics descriptions, some electromagnetism descriptions, what we knew about the atom, we were trying to essentially fit all of these pieces together, and if we could fit all of these pieces together in some way, could we recreate this graph? And the answer was no. Not at all. We were having a really tough time with it. There are two different competing theories here. You'll notice that the Wien's curve fit was essentially this, it almost makes the right curve, but it's got this kind of weird lumpy bit. Let me do a different color so we can actually see this. It's got this like weird lumpy bit, and it also dove down too far beneath everything else when we're talking about the long wavelengths. So all of the infrared, the radio wave stuff, it didn't accurately predict what was going on there. The Rayleigh-Jeans law, on the other hand, very well predicted the long wavelengths. It matched all of that information very, very well, but it led us to something called the ultraviolet catastrophe. Let me write that out in some fun words here. So ultraviolet catastrophe was quite a fun thing here. Here was the idea. When we tried to recreate this with the Rayleigh-Jeans law, it essentially predicted that there was a nearly infinite amount of high-energy ultraviolet radiation coming out of every single object. So much so that if you lit a bonfire, the radiation from that would essentially melt your skin off. And arguably, that's not entirely untrue if you are in the fire, but this was assuming even if you were just standing next to the fire, you would essentially instantaneously be melted by all of the ultraviolet radiation coming out of this. Now, we have been dealing with fire for quite some time. As far as I know, nobody has simply melted by standing next to the fire. And the scientists coming up with this equation thought so too. The evidence was in our favor that perhaps, even if this description works fairly well for the long wavelengths, it's not accurate in a more widespread kind of view. And that was what we knew as the ultraviolet catastrophe, because it's essentially assuming that if this equation were actually correct, then we would have a catastrophe on our hands. We wouldn't be able to deal with anything that is remotely warm because of the sheer amount of ultraviolet radiation that would be coming off of it. So Max Planck came up with this, and he was looking at these and he said, okay, I know something is wrong. Let me work through the math one more time just to see. And he based a lot of this stuff off of what we knew from thermodynamics, focusing on many of those details. This is actually called the grand ensemble for a bunch of different particles all doing different things. So he was looking at this and he said, okay, well, if I take this grand ensemble equation from thermodynamics and I make some modifications to it, I put these couple constants in here in different places, then I have essentially a matching graph. I have something that lines up almost perfectly. So this was not based in necessarily any physics. It showed up somewhere, but it was kind of this idea of like, okay, so we have pulled electromagnetism, as we think of it currently, from thermodynamics. Parallel, but kind of separate fields. So there was a little bit of what's going on here? That sense. What's actually going on here that we're seeing something like this? And we found if we put in the right constants, so he used quite literally the guess and check method, that if he guessed and checked enough, he could get exact matches for every single one of these emission spectra. So that was a good first step. Then we started to look at this thing a little bit closer. We said, okay, if we plug in some of these variables, here's where we run into an issue. If we do this with calculus, that is to say, every single photon has a certain amount of energy, so our dE would be essentially coming from this right here, the energy per photon. Planck's constant times the frequency. If we take every single one of these things and we're scanning across every single frequency, then what we run into is the ultraviolet catastrophe again. The energy simply doesn't work out. However, if we instead don't do calculus, right, we kind of flip Newton off in this case and say summations are great for computers, summations are great for me. And if instead we take essentially every single frequency that might be having a certain number of photons, and we make this a little bit more discrete, then the math works out perfectly to recreate the spectra. Calculus doesn't work here. Infinitesimally small photons does not work. You have to have a discrete number of photons. This little n right there is a specific integer number of photons. And this was a really weird thing, because the math, on its face, you would say, well, a summation and an integral, right, at a certain point, they mean the same thing, don't they? An infinitesimally large number in a summation is exactly the same thing as an integral. And that was the whole point. It's not an infinitesimally small number of things going into the summation. It is a finite number of things going into the summation. And when you take that assumption, the assumption that there is indeed a finite number of photons actually being emitted by this, not an uncountable infinity, then you get exactly the recreation of what we saw from each emission spectrum. And we also got an exact equation that predicts what that spectrum would look like, based on these constants right here. And this is how we get a constant like what we call Planck's constant. You know, you do enough work in the field and you get something named after you. That's kind of the big deal with this thing. That's, you know, all of these things as we see them. The Boltzmann constant, Wien, the Rayleigh-Jeans law, all of those things are essentially, you do enough work in the field, you get something named after you. But we get this equation, and this is not an equation that you guys are going to use necessarily, right? Because notice what's actually going on here. This is essentially saying that for every single wavelength and temperature, you get the intensity at that particular point in the spectrum based on this big thing. Rapp's constant is like -1. That's I'll claim that one. But what we see in here is kind of an interesting thing, right? We've got this strange exponential kind of shape, and what this is basically doing is that we've got two pieces here. This is essentially combining the two pieces. If we're looking at what this equation actually is, it's two large chunks. We've got essentially the constant outside, which keep in mind that we're saying that the wavelength can change. We're scanning over every wavelength. So for certain wavelengths, this is the dominant portion. For long wavelengths, this is the dominant portion as we would see it. For those shorter wavelengths, we get something a little bit more on this side, where that tends to matter a little bit more. And with all this stuff put together, we can exactly recreate every single one of these spectra. And I mean, this was a revolutionary kind of thing because we had finally understood what was going on with this thing. This provided a lot of insight as to what was actually going on with these things. This was not something that we really completely understood what was going on at the time. We just essentially said, we have found a solution. Now, what the hell does it mean? Right? That was kind of a very surprising thing to find at the first point. We didn't understand it quite at the time. So, a little bit later, or I guess kind of around the same time, really, there was other evidence that something might be going on here. And I brought this one up last time, talking about what the photoelectric effect is, and let me give a little bit more detail on this thing. Now that we have seen some of these things, right, there's basically this idea that you can ionize atoms. Some atoms are very easy to ionize, some atoms are not super easy to ionize. That is to just like rip away an electron. One of the good ways to do that is that you shine light of high enough energy onto it, and that light of high enough energy comes in, hits the electron, rips the electron away from the atom, and then it flies off. This is known as the photoelectric effect. Photo for light, electric because it's electricity, electrons. And it was actually originally Heinrich Hertz that found this. He was shining some things around, and he noticed that he was getting some sort of current out of his metals when he was shining light at it. So we said, all right, well, this is fine, right? Because we know that light has energy, so it makes perfect sense that that energy goes somewhere, it hits the electron flies away. Perfect, right? We understand that. That's fantastic. Then it just depends on the light intensity, because light intensity should just be essentially summing up, it doesn't matter what energy the light is, as long as you've got enough intensity, that should work. But we ran into this issue. Only certain wavelengths of light actually did this. And more specifically here, it's not just certain wavelengths. The long red wavelengths, infrared, it didn't matter how intense the light is. You could have the world's strongest infrared laser shine directly on a metal, and you would never get any electrons out of it. But if you take a pocket ultraviolet laser light, you would get tons of electrons very rapidly. And this was a big deal, because this meant that it wasn't just based on the intensity. It's not just the intensity, because if it was just the intensity, then it didn't matter what color of light it was. But because it did matter what color of light it was, that must imply that there is some sort of discrete energy packet. The same exact discrete energy packet that Planck had to use to recreate the thermal emission spectra. And we called this energy packet a photon, because photo has been around for a very long time, right? Photo based on light, so photons, we end anything with a particle kind of thing, protons, neutrons, electrons, photons, it all lined up perfectly. We called these discrete energy packets photons, though. And each of these energy packets had an energy based on its wavelength or frequency, whichever one you want to work with. But this basically kind of led the way. This basically said, okay, well, if on a per photon basis, there is enough energy to rip away that electron, we see current. If there is not, then we will never see current. It doesn't matter how much energy actually hits there. It has to be the energy per photon that meets some threshold before we can start ripping electrons away. And I've got all sorts of fun things down in here that I'm not going to talk about right now. And I talked about this last time about how there was a cartoon that turned me into a physicist, and I really do mean that genuinely here. Read through this description. I'm not going to go through it right now. Watch this video, please. I think it's super cool. It bothers the crap out of me if you read that and watch that and you've got some very serious questions and concerns about the universe as a whole. Let's talk about it. I would love to go through some of those descriptions. But for right now, I'd like to work with this brand new thing. It's here in the slide. Just download the slide. I'm telling it to you right now. You don't need an announcement from me. And this is going to be in the recorded lecture anyway, so anybody that's actually going through and looking at the lecture should be able to see this stuff just fine. So, let's use that brand new equation that we just solved, that brand new equation here in blue. When measuring the energy of photons, it is useful to use a unit that is not joules. Joules are huge as compared to a lot of these things. So we like to use instead the electron volt, which is a unit that doesn't mean a lot to you guys right now, but next semester it'll mean a whole lot more. But basically, this unit of energy, 1 electron volt, is 1.6 times 10 to the negative 19th joules. So, you know, pretty tiny. I want you to find the energy in electron volts of a photon with a wavelength of 550 nanometers. And then I want you to determine the wavelength of a photon that has 7.5 kiloelectron volts of energy. And I'm going to give you just the next 3 or so minutes to do this one. Use that brand new equation that we just saw on the last slide. Namely, I'll write it out here just in case. HF or HC divided by lambda. Use this brand new stuff that we've got. Work on this thing. Let's come back in just a little bit and see what you got. All right. So let's go ahead and start taking a look. And I don't even need to dive into another one for this one. This one is hopefully even easier than it might look at first. Energy in electron volts of a photon with 550 nanometer. I'm even just going to do it right here. Go ahead and say, all right, the wavelength, I don't want this to be in 550 nanometers. I would like this to be in meters. I need it to be in standard units because the first thing that I'm going to do is find this in joules and then do the conversion. Notice here, when we're looking at Planck's constant, there it is, 6.626 times 10 to the negative 34 joule seconds. You might also be able to find the electron volt version of the constant, and in that case, you essentially can skip some of the conversion there. But because I've already got that value, what I'm just going to do is convert this real fast into meters, and the easiest way to do that is to not do any conversion at all. To just say 10 to the negative 9th, let the calculator handle where it wants to move that decimal. Bam. That's done. Now, I see a wavelength. I see one particular version of this equation that uses that wavelength. H and C are both constants. When I do something like that, what I plug in, and what I find, rather, when I plug that stuff in, is an energy of 3.614 times 10 to the negative 19 joules. 10 to the negative 19, 10 to the negative 19. This is a good sign so far. We do the conversion to electron volts, and we find an answer like 2.259 electron volts. Bam. So good so far? If we're looking at part B, it's this thing in reverse. We say, okay, well, electron volts are not quite what I would like to see. I've got 7,500 electron volts right here. The first thing that I would need to do is convert that over into an energy. And that turns this into 1.2 times 10 to the negative 15th joules, which is a significantly higher energy thing, but it is also an X-ray. So it is a very high energy kind of photon. This is not a super surprising thing to see. When we plug all of that in together, we get something like 1.657 times 10 to the negative 10th, or I like to have this in 165.7 femtometers. It's a pretty short wavelength. Right, if we're looking at this, this is like a 0.16 nanometers, trying to do those comparisons of where they show up on the scale. Or 165 femtometers. How do we feel? The in-class assignment wants it in nanometers. Hang on real fast. How did I go from joule to femtometers? That's not a conversion. That is plugging into the exact same equation that we just saw here. The energy as we would have it, flip it around. So this becomes wavelength is equal to HC divided by lambda, divided by E, not lambda. Lambda shouldn't show up twice in the same equation. Plug in that energy that we just found into that to pull out the wavelength. Now, let me check that in class just to be sure that I didn't goof something up here. And now Canvas is doing the same thing that mastering was earlier, the things that we love to see. Let me check the details one time just to be sure. Yes, it should be in nanometers. That should work totally fine. And I think I've rounded something slightly strange. So convert the femtometers. 0.1657 nanometers. No, that's fine. Do we feel all right with it all, though? All right. So, let's imagine here. Do you guys even know what an incandescent light bulb is? I ask that semi-seriously. They have been largely phased out at this point. They still show up in a handful of places. But I genuinely have to ask because we're getting close to that point. Every year, this question becomes a little bit less relevant. As fluorescent light bulbs, if it wasn't, and actually this would have been a lot worse, there was intended to be essentially a cease on all production of incandescent bulbs at one point. I think they're still made anyways now at this point. I don't think that followed through, but for a while, there was going to be essentially, we're halting all incandescent light bulb production. So listen, we were getting pretty close there. In a few more years, this question ages, it ages worse every single year. But anyways, why don't we use incandescent bulbs anymore? Because the way that essentially an incandescent bulb produces light is by getting really, 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 really hot. And it turns out that when you're doing something like that, just to produce a little bit of light, it's, again, kind of like turning on that stove burner like last time to just produce a little bit of light into the room. Most of the energy goes into heat rather into light. So what we get here is that 95 watts of a typical 100 watt bulb, that's like your standard brightness for an incandescent bulb, 95 watts of that are just infrared heat radiation. Not a super practical way to really produce light. And that's why LEDs are so incredible, because most of that goes to actual light production at that point. But that's beside the point. Let's focus in on that 5 watts of visible light that we actually get out of this thing. If the average wavelength of visible light is right around, say, 600 nanometers, right around yellow, simplify the assumption, it's all at that wavelength rather than actually looking at the full spectrum. Let's just assume it's all that one particular wavelength, 600 nanometers. How many visible light photons does the bulb emit per second? Some fancy equations to help you down there at the bottom. Take the next 3 or 4 minutes. See if you can come up with an answer for this one. All right, are we ready to dive in with this one? I ask as if expecting an answer, but I move forward like I'm not. So, let's imagine here. We have 600 nanometer photons coming out. How many of them? That is for us to find. Energy per photon is going to be coming from this equation right here. So how much energy do we have coming out in total? Well, there's a couple different ways to write that. That's kind of the link between these two. See, a description like 5 watts, a watt is a joule per second. It just so happens that we are focused on 1 second at a time. So how much energy do we have coming out every single second? Well, 5 watts per 1 second is 5 joules per second. 5 joules. Where does that energy come from? It is not equal to this right here. That is implying that one single photon would have all of that energy, and that photon would destroy the first thing it touched. So much energy in a single photon like that, it would absolutely destroy anything it touched. It would just rip it to pieces. So that is not what we're looking at here. What we are instead focused in on is, let me label this E sub P. This is energy per photon. This is basically saying, okay, well, if it is energy per photon times the number of photons with that energy. So then, when we actually calculate this out, what we find, and actually we don't even need to do that. Let's just plug this thing in. Let's just plug this thing in. That's probably the easier way to do this, right? Less calculations. Energy per photon times the number of photons. What this turns into is essentially just HC capital N divided by lambda. Not lambda every single time. Oh, yeah, no lambda. That's fine. That's fine. Sorry, I'm getting myself psyched out now. Did that last time where I flipped lambda and E. I keep doing this. We're looking for the number of photons, so just divide by the 5 joules. Call this energy total. Right, as we would have this thing. Energy total, or I guess not divide by, but let's do it like this. Let me just do it like this rather than talking. Energy total times lambda divided by H times C is equal to the number of photons. This equation, combining those two things together. When we plug all of those numbers in, we calculate this out, we get something along the lines of 1.509 times 10 to the 19th photons. That is 10 to the 19th photons every single second, exclusively in the visible range. And only 5% of this energy is going into visible light. So there's a lot of photons. And this is kind of a standard, this is how many photons you expect to see. There's a lot of photons. Do we feel all right with this problem, though? And the whole big thing surrounding LEDs, and even to a lesser extent fluorescent lights, is that essentially they're trying to produce less heat but the same amount of light. LEDs are really special for it because most of that is essentially just the gap in the LED itself is producing most of that light without very much heat. You can try to reduce the heat of an LED as much as possible, but if your light bulb never gets warm, then it never produces, or the incandescent light bulb never gets warm, it never produces light. So by their very nature, you can't have an efficient incandescent bulb. It just doesn't happen. But you can have very high efficiency LEDs and fluorescence to a lesser extent. All right. So, all of this information was coming around the same time that we were beginning to understand the atom just a little bit better. Because at this point, early 1900s, we didn't have any real idea. We had some idea of what was going on there, right? You might have gone through any sort of just a general science course, might have gone through a little bit of the history. You might remember words like the plum pudding model and stuff like that, and other nonsense things that we talked about as we were trying to understand what was happening with the atom. We had essentially two big ideas at this time. Atoms are small. That's why we haven't seen them until now. But they are finite things that exist. Two, atoms are electrically neutral, but they certainly do contain negative electrons. We knew both of those things pretty well at this point. Right? Because realistically, we had separated and understood the electron at that point, and we knew that electrons must be part of atoms because sometimes we can essentially isolate those electrons away and make the atoms no longer neutral, but now ions instead. But we also had an idea here, kind of assumption, perhaps, that atoms emit and absorb electromagnetic radiation. Which means, that's the nerd way of saying light. They emit and absorb light. How do they do that? Do they have tiny filaments on the inside and somebody flips a switch and suddenly it turns on for just a little while? No, not at all. But we had started to categorize many of these different things by putting them in different situations and essentially seeing what becomes of the light that either comes from these things or, in another sense, is produced by them. So sometimes if we zap them with electricity, then we would get essentially the emission spectrum. If we heated up some sort of lamp or created a fire or some sort of white light source and put the element in front of it, then it would absorb from that full emission spectra the colors in particular that it really, really liked. So two different ways to run the same experiment with hydrogen. If you zap it with electricity, you get these top things. If you shine a white light behind it and then pass it through the hydrogen, you get these dark lines in the full color spectrum. And then to actually make this happen, of course, you wouldn't be able to see this normally because it would just appear as either a mixture of colors if it was electricity, or it would come as essentially you wouldn't notice the difference if it was shining through a white light. But if you pass it through a diffraction grating, that fun thing that we talked about last time, then that spreads out all of the different wavelengths. And suddenly you can notice these things. And you notice these very, very thin spots of either color or darkness, depending on which experiment you're doing. And this was interesting. But it was one of those things that were like, yes, this is here. Why is it here? What is it doing here? And we didn't have a definitive answer at the time. And realistically, there was not necessarily any sort of good description as to why this stuff was there in the first place. What we did start to notice, though, is that for some of these things, there was maybe a little bit of a pattern. And here's a general question for everyone. What is a physicist's favorite atom? Not talking to the chemist, talking to the physicist specifically. What is a physicist's favorite atom? Any guesses? Don't just guess what. Any guesses? Hydrogen. Of course it's hydrogen. Do you remember how complicated a three-body problem is? Disgusting. Hydrogen, though, is two bodies. One proton, one electron. That is very easy to talk about. We can have definitive equations that describe that interaction. So, we studied hydrogen. We said, what happens with hydrogen? If we can understand hydrogen, maybe, just maybe, we can extrapolate some of that understanding onto some of these other atoms. And in fact, if you're looking at the first column of all of the atoms, physicists love that entire first column of the periodic table because they all behave a lot like hydrogen. All of my research was done with rubidium. The other people in my field will use either cesium or sodium, those things that essentially behave a whole lot like hydrogen. Very easy to deal with. The running joke is that chemists asked the physicists for help and they said, hey, can you help us understand these atom things? And the physicists solved hydrogen, and then they looked at helium and said, okay, we did our part, now it's back to you. We didn't want to deal with it because it was more than one part, or more than two particles at that point. But we focused in on hydrogen, and I've got a lot of different things here, so let me go into a slideshow to see if this helps at all. Let's see if I'm in a good spot in the first place. So, oh, and we still can't see this. Hang on. I got this. There we go. As is tradition, somebody in physics looked at hydrogen and took a wild guess. He noticed something in particular, that all of the energies, as we could see them, or not all of them, but the visible spectrum in particular, had this fun relationship. Right there. And actually, if I remember this correctly, Balmer was not actually like a professional scientist in the same sense. This was kind of a fun thing if I remember. I want to say he was... what was he doing at the time? I think he was just being a teacher and a mathematician at the time. He was not necessarily super involved in research, but he had a kind of a fleeting interest in some of this stuff and dove in and made a huge contribution to the field. Being a nerd like us, absolutely cool. Careful there who you're calling a nerd. Come on now. But, so it's kind of fun things like that, right? Sometimes random people that you wouldn't necessarily expect in the same way. I'm not saying that to like discredit him by any means. He made a major contribution here, but anybody can contribute, right? It's always a fun thing like that. Everybody working together to pull that information to get something out of this. But he essentially guessed this equation that perfectly replicated the visible spectra of hydrogen. We saw these lines, which are lines that you can see, and notice that there's kind of the ones right down here beneath me. There's just a handful of them. They're a little bit dim though, but I don't have another spot to be on the screen because I'm about to show some other stuff here. So what we noticed in particular was that the Balmer series was specifically for the visible light. And now keep in mind here that lowercase n is allowed to be essentially any integer. Any integer you could want it to be would fit in here. If you plug in that N naught is 1, then you get the Lyman series in ultraviolet colors. So there is some sort of spectra way over on this side. You can't see that. Way over on this side. There is the Paschen series in the infrared when you plug in N naught is equal to 3. And of course, you can plug in any integer. You can do N naught is equal to 4, N naught is equal to 5, but all of those get more and more and more infrared as you go along. The Balmer series, when you plug in that it's equal to 2, you get this visible spectra that you can see right here. So in these, where essentially you plug in your N naught, and then you plug in every single other N, and that tells you where the color is going to be, where that specific line is going to show up. And what we have discovered as to what this is essentially transitions between the electron shells. Right? So the largest energy jump that you can possibly get is when you're going from the lowest energy up to some of the others. Right? So N1 to N2 is already a pretty significant jump, but if you're going for like 4 to 1, that's a pretty significant jump. That's why this is all in ultraviolet. The Balmer series is anywhere 2 to 3, 2 to 4, 2 to 5, 2 to 6. And that's why if we go back a step, we notice that there's kind of like this one lonely red all by itself, and then we've got the cyan, and then we've got a couple of these purples all grouped up together. Largely because we've got our red, we've got our cyan, and then the purples get grouped up closer and closer and closer. The infrared is at that point essentially the smallest jump. So they're getting smaller and smaller and smaller just like that. Now, N technically goes out to infinity. If I move myself a little bit here so we can see what's going on in that top, N technically goes out to infinity. However, it gets smaller and smaller and smaller. It reaches a limit. And that limit, the most energy that you can get out of a hydrogen atom is 13.6 electron volts. If you go any larger than that, then you no longer are going to be emitting light. You are going to be emitting electrons. You have ionized the electrons in the hydrogen atom at that point. Right? It's just too much energy and it completely rips the electron away. But anything less than that will show up somewhere in this massive spectra. So there's some fun things with this. And in fact, there's actually a bit of interest into what's going on with the, oh no, how did I get back to this? There's actually some interest in these really, really high N numbers. If you are at all interested in what goes on with that, atoms behave very strange, and they have a special name. They're called Rydberg atoms. The Rydberg atoms are all about what happens when you're like N is equal to 50, and those super far out, almost ionized kind of atoms. They've got some kind of unique properties for being all the way out there. So just some fun things on that, if you're at all interested in some of the cool things that go into all of this. But this was kind of a discovery through guessing more than anything else. Very much like what Planck had done on looking at, essentially, I'm trying to find some sort of equation that answers this. And then after the fact, we can try to look at that equation and, eke out what actually might be going on here. So let me actually get out of this. Discard those annotations. We don't need all that stuff. So you have probably seen a picture like this before in your science history of some form that you have gotten, I assume. But even if you haven't, that's not a big deal. Basically, we had this old description. Plum pudding model was a reasonable description at the time because it said, okay, well, the atom is there, and then the electrons are contained inside of it, and this whole thing can do things, but it kind of made sense, but not really, because the spectra didn't line up. It didn't make any sense that the spectra would go like this if the plum pudding model was actually accurate. And there were other things as well that were a little bit strange about the atom that didn't line up with this description, but this was, a first guess, not a bad guess, but it wasn't quite accurate. We knew some things were going on with this. So one of the other big issues with this, and really what kind of put the final nail in the coffin for the plum pudding model, was this idea that we got from the Rutherford scattering experiment. Now, you might be familiar with this one, but here's the idea. We took a really thin sheet of gold foil, and I mean like atoms thick of gold foil, extremely thin, and we threw a bunch of alpha particles at it. And alpha particles, more or less, are just, helium. It's helium atoms, but without their electrons. So an alpha particles are really easy to get from radioactive samples. So you essentially have some sort of radioactive sample, and you just turn it, and it sends a bunch of alpha particles that way. Then we put a screen around this thing, all the way around it, in fact, to see essentially, okay, well, when the alpha particle hits the gold foil, if it deflects in some way, then it should light up the screen. That high energy collision essentially just lights up the screen. It's made of phosphorus or something else like that. And the expectation was here that we're probably going to be reflecting a lot of these things back off. But what we found was really strange. It wasn't that it just deflected. It wasn't that it deflected off of a bumpy surface and went in a few different directions. It's that most of the particles went directly through. But some of them did get deflected. And that was troubling. It was incredibly troubling because this told us that most of the atom is empty space. How else could an alpha particle possibly just fly directly through and not touch anything, but on a rare occasion be deflected back, a very high energy alpha particle being deflected back perfectly and hit somewhere behind it? Most of the atoms had to be empty space, but there had to be some very positive charged core directly in the middle. What we now understand as the nucleus, where all the protons and the neutrons are. So, let me go through all this real fast. Do you recognize this equation? You should. It's gravity, right? As it turns out, electromagnetism behaves a whole lot like gravity. In fact, it was kind of those two were inspired by each other. The force is now, instead of using G-M-M over R squared, now it is K Q1 Q2. Sorry, I just had a cat run in front of my window. Quite distracting. Q1, Q2 are the charges of each particle rather than the masses. And we can take that exact same description as we had with gravitational potential energy to essentially find the gravitational, or not the gravitational, the electric potential energy of two different particles. Instead of capital G, we use this Coulomb constant K, 8.99 times 10 to the 9th. And this was like 4 weeks of 192. All of this information right here. If you can master this stuff right now, you've got your first exam, or not your first exam, exam 2 down. But anyways, let's look at something here. An alpha structure, an alpha particle with kinetic energy 8 mega electron volts, so that is 10 to the 6th electron volts, rebounds at 180 degrees from a gold nucleus. What is the alpha particle's closest approach to the nucleus? And some of the hints that I will give you here, see the constant sheets for some of these values, but I can just feed these to you directly. Basically, what we've got going on here is that we know that the mass of a alpha particle, as we would need it, would be 4 times the mass of the proton. The mass of the proton is, I thought I wrote this down somewhere. Oh, we don't actually need it. Never mind. Just kidding. The fundamental charge, as we would see it, is 1.6 times 10 to the negative 19, a number that you might recognize from a few slides ago. And there is a reason for that, but not one that we can get into right now. And is there anything else you need? That value, K, 8.9 times 10 to the 9th. I'm just writing some of these things down. They are all essentially on the last slide or your constant sheet, but just to make your life a little bit easier. Q1, Q2, that is the charge of each particle. Kind of like mass, but a charge instead. R squared, potential energy, same thing, but reversed. Not R squared, just R. Some equations, some values that might be a little bit helpful for you here. But I want you to take the next handful of minutes here, say 3 or 4, come up with an answer. How close can these two particles get before the alpha particle gets deflected all the way backwards? Give it a shot. Okay, so let's go ahead and try this. Here's what we've got. One of the big things that I should have mentioned in a little bit more of a detail, but perhaps you know this one already, is a phrase like opposites attract works perfectly for electromagnetism. So whether or not it's real in like people and things like that, which arguably it's probably not actually true, but that's beside the point. For electromagnetism, it very much is the case. Opposites attract, like charges repel. So if I have an alpha particle consisting of protons and neutrons, and I have a gold nucleus consisting of protons and neutrons, those two sets of positive charges really don't like each other. They don't want to be anywhere near each other. In fact, it takes a whole lot of energy to shove them together. It's a bit like taking two north sides of magnets and trying to shove them together. Anybody that has tried to do this knows that as you get closer and closer and closer, suddenly there's this really big force kind of stopping the two of them from actually meeting together. They're very unhappy about being in that position. Much the same way, two positive charges don't want to be towards each other. So, here's how we have to imagine this. It's a potential energy. All of the kinetic energy that we start with eventually will be converted into what we call electric potential energy. Now, the easiest way to do this is to say, hey, don't we start with a value for that kinetic energy anyways? So this is 8 mega electron volts is equal to K, Q1, Q2 over R, the distance between them. Solving out for R. Q1 is going to be 4 times this number E. Q2 is going to be 79 times this number E. K is that value that we've got from here. Plug it all in together. R is equal to K, Q1, Q2 divided by that kinetic energy. Plug in all of those numbers together, and what you get out on the other side is something like, where did I write this? On the other side of this page. 2.84 times 10 to the negative 14 meters. A very tiny amount. But why is it 4 and not 2? Because I can't do calculations properly. That's why. It should absolutely be 2. Hopefully I didn't screw that up in my solutions. I just screwed it up here. It's called supercharged helium. It's got 4 protons instead of 2. That's not a real thing. As far as I know, there's only one stable isotope of helium anyways, and 4 would not be, 4 would be something else by that point anyways. Most helium has 4 particles in it though. 2 protons, 2 neutrons. Some helium only has 1 neutron. And if you're looking at that, it's around $10,000 for a liter of it. It's extremely expensive to get helium-3. Femtometers, what is that? Femtometer is a 10 to the negative 12th. So 10 to the negative 14 here. Canvas question says it's 10 to the negative 15. Hang on here. Did I goof something up? Let me see. An answer is of 10 to the negative 15th when we're talking about femtometers. So it's not that this answer is incorrect. It's saying that if it was in units of femtometers. And again, this is stuff that you'll cover in a little bit more detail in 192, talking about these things, after a healthy jog through all of thermodynamics. And when I say all of thermodynamics, I really mean just the most applied parts of thermodynamics. And then diving into the fun stuff, like what we've got in electromagnetism after that. So it was just kind of a fun little thing here to see essentially what kind of distances would we be working with? What might this start to look like if we needed to do some of these kinds of equations? And we get stuff like this, right? These are incredibly tiny distances, but that's a lot of what actually goes into dealing with these particles. But now the fun thing about this is for something like this. So this is basically saying that I can fire these alpha particles with tons of energy. So much energy that, this description in here about a 15-inch shell, that is not a seashell. That's a tank shell, right? Fired from a tank, a massive bullet is what he's talking about here. That's how much energy, relatively speaking, we're talking about these alpha particles having. And the closest it can get is 28.4 femtometers. How large is the gold nucleus in the first place? And I'm actually kind of interested because I'm not entirely sure what I have for this. The nucleus is on the order 10 to the negative 14th as well. So this thing gets about 1 radius away, and it took 8 mega electron volts to essentially get us there in the first place. So for something like this, what that generally means here is think about all of those protons that are actually inside of the nucleus in the first place. What holds them together? Do we know? Because it's certainly not electricity, right? Electromagnetism would suggest that all of these positively charged particles would want to fly apart rapidly. And it is indeed what we call the strong force. Gravity is not nearly strong enough to make this happen. Gravity is the weakest of the 4 forces, actually. Gravity is an incredibly weak force. We run into this issue a lot, but the strong force is a special, unique force that deals on the atomic scale. It doesn't expand outside of the atom. It's a very, very, very short-range force. It only essentially works on the size of the atom itself, no larger than that. It trails off too quickly. I think it goes as something like 1 over r to the 12th, if I'm remembering correctly, roughly. But it's responsible for holding these very unhappy particles all together. And that's why you need neutrons there for stability, because neutrons don't have any electric charge, but they do interact with the strong force. So they're like the extra little bit of glue to hold all those protons together. So some cool particle physics to mix in with all these fun things as we're talking about them. So let's take a little bit of a breath here. Let me hit you with a little bit of history, because I think history is a fun thing to talk about in this case. 1900, Max Planck was trying to explain black body radiation, and I am just going to read off the slides on these ones. Apologies if you hate that. He modeled the black body as a cavity radiator and found that he could successfully reproduce the continuous spectrum if and only if he assumed that the cavity emitted and absorbed radiation in integer multiples of discrete quanta with energies given by E equals HF. Basically saying, we need photons. We know there has to be individual packets of energy given these different values. Einstein took Hertz's experiment about the photoelectric effect and applied Planck's description of packets of energy to what we were seeing in the photoelectric effect. Hertz couldn't explain the photoelectric effect. He didn't understand the results that he had in hand. But Einstein, having read Max Planck's work, understood that these two must be related in some way. And this was actually Einstein's first kind of big come-up in popularity. What really put him on the map, it wasn't just the E is equal to mc squared stuff. It was actually his description of the photoelectric effect. By explaining the photoelectric effect using Max Planck's quanta description, quanta meaning like discrete values, we had a complete description of why it only worked with certain colors of light. And then with Rutherford, he understood that there must be a nucleus there. And if there must be a nucleus there, and it is not electrically neutral, big deal there, that tells us that there must be a bunch of different electrons orbiting on the outside of that. Now, here's a thing to think about. How do antennas work? You have one probably in any device that you're working on right now. I have to imagine, unless you've got your full-on maxed out gaming computer with hardwire Ethernet connection, I have to assume most of you are running on Wi-Fi. If your computer's not running on Wi-Fi, then your phone certainly is. How does that work? What goes into an antenna? Does anybody know? Is it just a big light bulb, or not quite? So I'm fishing for an answer here, and I think I'll just give it to you to make sure we've got time for everything. Here's the idea. When I take a charge, like an electron, and I wiggle it around, it emits light, usually at the same frequency that it's wiggling, which means that a big radio antenna is essentially just shaking those electrons back and forth at that frequency that they're putting out. And slight changes to the wiggle, you can essentially encode that as information. So that presents a little bit of a problem. If I have a wiggling charge, it produces light. So this model of the atom that we produced, we essentially immediately knew it could not be true. I know this is the common way to view atoms. I know we've got a very clear understanding that this is what atoms look like, but we knew essentially when we made this picture that it could not possibly be true. But it fit. Based on all of our understanding at this point, this was really the best answer we had, even knowing it was wrong at the time. The electrons, as they would orbit around, must be accelerating. If they must be accelerating, then they must be shining out light. If they are shining out light, they are losing energy. If they're losing energy, they're going to crash into the atom. And at that point, we wouldn't have atoms anymore. We would just have neutrons everywhere, or constant explosions. And that's not actually what happens, as far as we know at least. So we knew this couldn't be it right off the bat. But what if, just maybe, we could patch this up in some way? What if we said that electrons can only have certain energies in the first place? What if this orbiting idea, they can't just orbit anywhere? What if they're only allowed to be in very particular places? And this was not just pulled out of thin air, because realistically, for one, we had already looked at things that were quantized. Light wasn't the only thing that's quantized, but also, I mean, let's go back to what's going on with this. Clearly, there's some sort of pattern here. We were trying to describe this in the first place, talking about maybe it's like a spring or something else like that. What frequencies could it oscillate as a spring? So this was not an unfounded kind of idea. This was very much kind of working along the lines of everything that we've been seeing so far. Where does this lead us? Don't know why that's down there like that, using some of Einstein's ideas. Make that look a little bit nicer while we're here. So he came up with this idea, okay, what if there are only very particular orbits of the electron around the atom? 1, 2, 3 discrete quantities just like that. Then, assuming here that each of these frequencies of light that comes out is in some way related to transitions between these levels. And each of these levels would essentially have some sort of angular momentum by the fact that it's spinning around, in a sense. Could we combine all of these things together into one complete description? And the answer is, of course we can. And we're going to do it ourselves. Here's what we've got. I'm going to work with this one through you. I would recommend go ahead, do this kind of alongside of me. I'm going to talk about each of these steps as I go through them. But here's what I'm thinking. We want to go through this complete description. What we're going to start with here. Use what you know about uniform circular motion to find an expression for the square of the speed of electron in terms of physical constants. That is, let me take what I just saw from a few slides ago, this thing right here. I say there's an electric force, kind of like gravity would be, to keep these two things together. And gravity is so incredibly small that I'm not even going to consider it. It's really not worth it. So there's an electric force keeping me in my circular motion. Let's start there. We have a circle. Amazing. We have a nucleus in the middle. Who cares about that thing? We have an electron on the outside. And I'll label it electron. And we'll just call this proton. Right, just so we're on the same page. And I'll even do a P plus. Actually, P plus is fine. I was going to say positron, that's a different thing. So let's say that this thing is moving around. Oh, shoot. Yep, you're absolutely right. Bam. There we go. No groundbreaking things quite yet anyways, so this is fine. Actually, in fact, let me even just go to this picture. That way I can jump back and forth a little bit easier. Let's say that it's moving around at some velocity. It's got some radius, all of that common information that we see with a circle. So that is to say, if it is moving in a circle, then it needs to have a centripetal force, where this is the mass of the electron, velocity squared, divided by r. What provides that electric force, or that centripetal force, is the electric force. K, Q1 is negative E. And in fact, let's just do this with magnitudes. Let's just do this with magnitudes for now. So this is essentially the electron, the proton, divided by r squared. And I'm doing this with magnitudes because opposites attract means that it's attractive. The negative sign in there, we're not going to worry about it right now. We're looking to solve out for v squared. So we move r to the other side. We move m to the other side. What we get, v squared is equal to k e squared divided by m times r. Okay, so far so good. That's step one. Step two, use Bohr's angular momentum postulate that basically said electrons can only have very certain angular momentum. Obtain another expression for the speed of the electron. Okay, so what an electron is a point mass orbiting about the nucleus. What that means is if we use that angular momentum description, right? Let's look at this thing. We are a point mass. How much momentum do we have? mv. How far away from the orbit point are we? Times r. Do I have to worry about the cross product right here? Yes or no? What do we think? No, but why not? Been a little bit cheeky there. Apologies. It's a 90-degree angle between the radius and the velocity. So it's just a sine of 90 anyways. So I'll even consider it though. Let's just go ahead and do this thing. Let's say that we have to go with this thing, but it just turns out it's a sine of 90 degrees. It's a right angle between the two. So this just becomes mvr. But we said this is perhaps discrete quantities in h bar. Okay, a little bit strange, but let's work with it. Then in this case, if we were to solve out for the speed here, we would say that v is equal to n h bar divided by m r. Where again, n is just essentially some measure of which orbital are we in. Are we in the first one, the second one, the third one? Which shell? Okay, so with all of this information so far, now what we're going to try to do is relate these two values together. Taking what we have seen so far, we're going to say combine the expressions for these two to find an expression for the allowed orbital radii of the electron. Because really what we're saying here, if we're looking at our top equation right here, basically what we're saying is that, okay, well, some sort of relationship between these two, we know there has to be a certain velocity for a certain radius, but our angular momentum equation is basically telling us you are only allowed to have these combinations of those values. It can only be n is equal to 1, n is equal to 2, n is equal to 3. They must be discrete quantities. The electrons can't just be anywhere. So when we combine these two together, do something like this. I'm going to square my expression down at the bottom. So I'm going to get n squared h bar, h or h bar. I've already forgotten, h bar. Where h bar is really just h over 2 pi. It's such a common expression that we have its own symbol for it. Probably more commonly used than h, if I'm being honest. N squared, h bar squared, divided by m squared, r squared, is equal to k e squared divided by m r. So far, so good. So let's combine some of these things. What I'm going to do is, well, first, let's cancel out some of the m's. Let's cancel out some of the r's. And then I'm actually going to multiply this r over. I'm going to multiply both sides by r now. So when I do that, here's what I end up with. n squared h bar squared divided by m is equal to k e squared times r, because I'm trying to solve out for these different radii. Divide by k e squared. The allowed values for r are going to become n squared h bar squared divided by m k e squared. And what I'm going to do while I'm here, I'm going to add this little subscript n to r. That's basically saying that I can find every atomic radii by plugging in just different values of n. The mass of the electron doesn't change. The Coulomb constant, K, doesn't change. The charge of the electron or the proton don't change. The only thing that's allowed to change here is this value n, so this tells me where my allowed radii are actually going to be. So, what are they? let's actually plug in these numbers and find them. In 1, 2, 3, let's plug those values in, and what do we get? When we plug in those values, here's what we end up with. R1, plugging in all of my numbers together, gets me something like 0.0529 nanometers. So remember here what I was talking about, the femtometers, 10 to the negative 14th is about the size of the nucleus of the atom. So this is going along the order of 10 to the negative 11th, a few orders of magnitude larger than the actual size of the atom. That's how far away the closest electron is. Pretty significant difference. R2, on the other hand, is going to be something like 0.2116 nanometers. R3, going to be something like 0.4761 nanometers. And if you notice this relationship between them, it's all coming from n. So when n is equal to 1, 1 squared is just 1, 2 squared is 4, 3 squared is 9. But they're all related by essentially this number otherwise. H bar squared over mke squared is 0.0529. Multiply it by 4, multiply it by 9. That's how we get these other two values. So when we're plotting these things out, if I try and do 1, 2, 3, 4, 5, 6, 7, 8, let's imagine that these are actually well spaced out. Here's my nucleus. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's about what those orbitals look like. Roughly speaking. I know this is a very bad drawing, but those are essentially where we imagine the first 3 spacings of those electron shells to be for hydrogen. So, we're not done yet. Write out the total energy of an electron as the sum of its kinetic and potential energies. Use what we've got from the previous steps to make this happen, okay? So we're getting close here. Basically, all we need to do at this point is we need to say, okay, well, these are the allowed radii that we could have in the first place. I'm going to kind of write this one special in case we need this thing for later. But here's what I'm thinking. The energy that we've got, there's an electric potential, there's a kinetic energy. We're just focused on what the electron is doing. So the total energy of the electron would look something like this. 1/2 mv squared plus, now this one's going to be a little bit strange because it's a potential energy. Where would the electron like to be? Close to or very far away from the nucleus? Not far. It wants to be as close as possible because in this case, the electron and the proton have opposite charges. Opposites attract in this case. The electron and the proton are held together by the electric force. They want to come together. Which I know we're jumping through this one, so it's a little bit confusing on this. It's like charges. When it was the alpha particle and the nucleus, both of those were positive charges. They didn't want to be together. That's why it was a positive potential energy. In the case of the electron and the proton, they've got opposite charges, so they would like to come together. They are going to have a negative potential energy because remember that it wants to slope downwards. It wants to go to the lowest possible energy state. They would like to collide. Quantum mechanics doesn't let them. So this is going to be a negative k e squared divided by r. With this, what we're going to do is I'm just going to take probably the easiest way to do this one. Let me go back up to my description of what I had for v squared in the first place. Let's say for v squared, we had this thing as k e squared divided by mr. Let me plug it in here. So what I get is 1/2 m k e squared divided by mr minus k e squared divided by r. The m's cancel out, and what I'm left with, in red please, make it a little bit more distinct, 1/2 k e squared over r minus 1 k e squared over r. What I am left with is the total energy is a negative 1/2 k e squared over r. It's a little bit strange here, but that's all right, because now what I'm going to do, my last step, is let me take this description for r, because we said there's only certain radii that are actually allowed to be there. So we plug it in. And we get kind of a nasty thing at this point. Here's what we're going to do. We're going to say negative 1/2 k e squared divided by, and let me do this thing in a parenthesis to say this mess, n squared h bar squared divided by m k e squared. Yikes. Got a lot of different things going on in this one, but that's all right. So here's what we're going to do. We're just going to essentially flip anything on the bottom here, move it up to the top. Negative 1/2. Now this is going to become m k squared e to the 4th divided by n squared h bar squared. With all of this, when we plug in for what n is equal to 1, what that energy would be, plug in all of our numbers, we end up getting exactly negative 13.6 electron volts. The ionization energy of hydrogen, the lowest energy state of the electron orbiting hydrogen. And this match right here was it. That said, we've got it. We're on it. We've got the number, because we've experimentally demonstrated this number already. If we go back to that description of what we had from before, we have seen this number show up. This is not a new number for us. No, it looks like it is right here, but let me move this to the back. Does that make it any better? Kind of. We have seen this 13.6. Notice it right up here at the top. We knew that was the ionization of energy of hydrogen in the first place. So when we had gone through this description and found 13.6 electron volts again, that was it. We have our answer. The electron is quantized around the atom. There are only certain shells, only certain places that it's allowed to be in. Now, when you start to get into the more complicated atoms, meaning anything but hydrogen, you've got a lot more complex details, because at that point what you've got are multiple electrons existing in multiple shells. Even hydrogen is technically a little bit more complicated than we're making it out to be right now. It's the difference of things that we call like the fine structure and the hyperfine structure. Details that are quite a bit more complicated than just what we're talking about here. But at the very least, we have a broad description of what the atom is doing, and we have a definitive understanding of what the electron must be doing spinning around that atom. And this is kind of our proof, in a sense, that the electron is, in a sense, spinning around the atom. You might know, because you're clever, that it's actually existing like a cloud around the atom. It's not in any one place at any one time, and that is kind of true. It just turns out that not only is energy quantized, so is momentum. And that makes it a little bit more tricky. Why are we using that fancy h? Just because that's the one that shows up more often than not, actually. That's just defined right here. H over 2 pi. H bar. Yeah. It shows up frequently enough even more frequently than the regular Planck's constant, that we've given it its own symbol. Rather than writing h over 2 pi every time, we just write h bar. So in summary, this was our description. This was our understanding of the atom. And this is that joke about chemists handing hydrogen over to the physicists. This is what we were able to come up with. And then we looked at helium and we said, never mind, no thank you, we had our fun, and passed it right on back. And I'm saying that as if they are completely different camps. They are not completely different camps. Physics, chemistry, biology, it's all science at the end of the day. We're all looking for answers. That's why a mathematician was able to come up with the Balmer series, because we're all working together at the end of the day. We're all just trying to find these answers. I am not at all going to get into superiority complexes in science or nonsense. I make jokes about it sometimes, but superiority complexes in science are absolute nonsense. Rutherford was actually really bad for that one. Rutherford had a real superiority complex. Everyone is looking for answers in different things. And that is all very worthwhile. So that's it. That's the atom. Or at least hydrogen. So, hopefully you had a little bit of fun. I personally loved this stuff. This was essentially what got me drawn into science in the first place, is when I was looking at a lot of this stuff and I was just fascinated by it. Essentially how we got through all of these things, the equations that we saw, why things were quantized. And I still don't have an answer for that one. But there's all sorts of really cool stuff here that I absolutely adored. Again, a quick reminder as I am closing out with all of this stuff, I do have one of these slides. In these descriptions down here, I've got all of this long stuff. If you'd like to read a little bit more about some of my thoughts, if you'd like to dive into this stuff, and a very, very neat video that I do highly recommend you watch, it's a fun watch, right? It's a cartoon. It's like quite literally aimed, I think, at kids. I don't know why you would try to show the double slit experiment to kids, but that's not for me to question at this point. I love the video myself anyways, and I think it is a exceptionally accessible kind of description as to what actually goes on. So, that's all we've got for right now. We've got one more actual lecture. Quantum 3 is going to be on Monday now. At that point, we will essentially finish out our description of the nonsense by looking at things like de Broglie waves. And the weirdest part, essentially the clap back from light, of making light have a particle description. Light claps back at us and says, okay, well now all of your atoms have wave descriptions. And we'll get into that a little bit on Monday. But for right now, I hope everyone has a very fantastic weekend. The link is broken. I'll scream. There's no way. No, they made it private. Okay, hang on. I can find this. I can find this. Dr. Quantum's got a lot of fun videos. Oh yeah, that's that sweet, sweet 480p quality. Can I find one that's slightly better? None of these are good quality. This might be one of the better ones though. I'll slap a new one in here. I'll slap it in chat. Oh, not that. If you are very interested in that, that's what that thing should look like. Get that in there. Add. Yikes. So I think this one is actually a little bit longer than the one from before. I think it's got a lot of extra stuff at the beginning. I can't tell. Maybe it goes through two different things. But a super fun video and all sorts of extra nonsense kind of tacked into it. All in a fun little cartoony package. The things we love. Oh, and Twitch, if you were looking for this as well, you're welcome to have that. Okay, to the person that had said before, put it into an announcement, now I actually will. Okay. Announcement sent out just in case anyone is not here or anything else like that. Now it's actually updated for this, and it'll probably be broken again a year later. Because I'm pretty sure none of these are like legal uploads or anything technically. I imagine that every now and then there's probably some takedown or something else like that. But as it goes.